Reality contains a problem it should not allow. According to the rules that govern particle physics, the universe should have erased itself moments after it began. Matter and antimatter should have formed in equal amounts, collided, and vanished into radiation. If those rules were complete, there would be no stars, no chemistry, no observers listening to this sentence. Yet the universe is made almost entirely of matter. This is not a philosophical gap or a poetic mystery. It is a measurable imbalance written into particle counts, cosmic radiation, and laboratory data. For decades, physics treated this mismatch as a settled question, with an incomplete footnote. Recently, that footnote has reopened. New measurements have not created chaos. They have created pressure. The numbers coming back from precision experiments are small, quiet, and consistent. And that is exactly the problem. They confirm that the known mechanisms are not enough to explain why anything exists at all. The contradiction is not new, but its return is. Theories once considered speculative are resurfacing because established explanations are no longer expanding to meet the data. Instead of converging toward closure, results are narrowing the escape routes. Each refinement removes another comfortable uncertainty. What makes this moment different is not an anomaly screaming for attention. It is the absence of one. The universe behaves exactly as expected in most tests, except where existence itself is concerned. That normality has become suspicious. This is why scientific confidence is under strain. Not because something broke, but because nothing did. The laws still hold, the instruments still agree, and the gap remains. And that gap now sits at the center of a question science believed it had already framed correctly. One of the most trusted principles in modern physics is a symmetry known as CPT invariance. It states that if you reverse charge, parity, and time, the fundamental laws of physics remain unchanged. This symmetry is built into the mathematics of quantum field theory and has been tested across countless experiments without visible failure. Under CPT symmetry, matter and antimatter are treated as mirror counterparts. They should be produced in equal quantities and obey identical physical rules. When they meet, they annihilate completely. This is not a hypothesis resting on intuition, but a consequence of equations that accurately predict particle behavior to extraordinary precision. In the early universe, temperatures were high enough to create particle-antiparticle pairs continuously. As the universe cooled, those pairs should have annihilated each other almost perfectly. The expectation was not imbalance, but near total cancellation. Anything else would require a violation of symmetry. Physicists were aware of this implication long before they could test it directly. To account for the visible universe, a small excess of matter over antimatter was required, on the order of 1 extra particle per billion. That tiny difference is what allowed galaxies, stars, and atoms to form. To explain that excess, theories of baryogenesis were developed. They proposed conditions under which symmetry could be slightly broken during the universe's earliest moments. These conditions were precise, constrained, and seemingly compatible with known physics. For years, one mechanism appeared especially promising. Subtle violations of CP symmetry had been observed in certain particle decays. These violations showed that matter and antimatter do not behave in perfectly mirrored ways. It seemed plausible that this asymmetry could account for the imbalance. But there was a problem embedded in the numbers. The observed CP violations were real, but far too small. When calculated carefully, they fell short by orders of magnitude. They could not produce enough excess matter to explain the universe that exists. Despite this shortfall, the framework remained trusted. The rule worked everywhere else. Particle accelerators, atomic clocks, and quantum tests all reinforced the same structure. The violation appeared local and limited, not foundational, so the rule stayed in place. The imbalance was treated as a detail yet to be resolved, not a threat to the system itself. What has changed is that newer experiments are no longer expanding the margin for that resolution. They are closing it. The first response to the mismatch was to question the measurements. Could early universe conditions be misunderstood, or could current instruments be missing hidden variables? Precision experiments were designed to eliminate these possibilities one by one, not by speculation, but by controlled repetition. Particle accelerators pushed collision energies higher and detection thresholds lower. Detectors were recalibrated, upgraded, and cross-checked across continents. If an overlooked process was producing additional asymmetry, it should have revealed itself as experiments became more sensitive. It did not. Environmental explanations were tested next. Magnetic fields, thermal fluctuations, and background radiation were all examined for their potential influence on decay rates. Each factor was isolated, measured, and mathematically removed. The asymmetry did not grow. Statistical error was another candidate. Large data sets can create illusions of precision without substance. To address this, experiments were repeated over longer durations with independent teams. The same null results appeared again, consistent to uncomfortable decimal places. Even cosmic explanations were considered. Perhaps the imbalance was not generated locally, but inherited from unknown pre-inflation conditions. Models were adjusted to test whether inflation could amplify a tiny asymmetry into a large one. The math refused to cooperate. As the list of external explanations shortened, something unusual happened. The data stopped fluctuating. Instead of drifting toward a solution, results stabilized around values that were clearly insufficient. Stability in this context became a warning sign. Normally, null results provide relief. They confirm that systems behave as expected. Here, normal behavior confirmed the absence of a mechanism science required. The silence was not neutral, it was informative. By the time these checks were complete, the problem had shifted. It was no longer about missing noise or faulty conditions. The rules were being followed precisely, and that precision was the source of the contradiction. With external explanations exhausted, attention turned inward. The question changed from what conditions might have distorted the outcome to what assumptions defined the framework itself. The contradiction was no longer treated as a gap in data, but as a feature emerging from the structure of the theory. At the center of that structure is the standard model of particle physics. It is one of the most successful predictive tools ever built, describing fundamental particles and forces with extreme accuracy. Yet its success depends on constraints that were never designed to explain why the universe exists at all. Within the standard model, CP violation is allowed, but only in limited, specific interactions. The model treats these violations as adjustable parameters rather than emergent necessities. They explain observed decays, but they are not required to scale beyond them. This reveals a deeper issue. The model was constructed to preserve internal consistency and symmetry wherever possible. Any violation is introduced carefully, almost reluctantly. As a result, asymmetry is treated as an exception, not a driver of cosmic structure. When physicists attempted to extend the model, they encountered resistance from the math itself. Adding stronger CP, violating terms, often broke other successful predictions. Fixing one problem destabilized several others. The framework resisted modification. This resistance suggested that the imbalance problem was not missing a piece, but pressing against a boundary. The equations could accommodate small violations, but not the scale required for existence. The limit appeared structural, not experimental. Some researchers began to question whether symmetry itself was being overprotected. If the universe favors matter so strongly, perhaps symmetry is not as fundamental as assumed. That possibility challenges decades of theoretical intuition. Others pointed to how time is treated in the equations. CPT symmetry assumes time reversibility at a fundamental level, but the universe exhibits a clear arrow of time. Entropy increases. Processes do not reverse. The mismatch between mathematical time and physical time became harder to ignore. What emerged was a quiet discomfort. The theory worked too well where it should not. Its internal elegance prevented it from explaining its own consequences. That elegance, once celebrated, started to look like a constraint. The pressure did not come from critics outside the field. It came from within, from researchers who trusted the model enough to see where it refused to bend. Once the problem was recognized as structural, the implications became difficult to contain. If the known laws cannot generate the matter required for existence, then something fundamental is missing. Not a parameter, but a principle. One possibility is that additional particles or forces existed briefly in the early universe. These would have altered symmetry conditions long enough to create imbalance, then vanished without leaving direct traces. Such ideas are mathematically viable, but experimentally invisible so far. Another option challenges the assumption of absolute symmetry itself. CPT invariance has never been observed to fail, but it has also never been tested under the conditions where the imbalance would have formed. If it breaks at extreme energies, the foundation of quantum field theory would need revision. Some researchers are forced to consider whether time behaves differently at fundamental scales. If time asymmetry is built into reality rather than emerging statistically, then matter preference could be a consequence, not an exception. This would reframe entropy, causality, and reversibility at once. Others look toward cosmology rather than particles. If the universe contains regions with different symmetry outcomes, our matter-dominated region may not be typical. That idea preserves existing laws but weakens their universality. Each of these possibilities carries cost. They threaten the predictive closure of current theories. They introduce elements that cannot yet be tested directly, and they blur the boundary between explanation and speculation. What unites them is not confidence, but necessity. Scientists are not choosing radical ideas because they are attractive. They are being pushed toward them by constraints that refuse to relax. The pressure comes from knowing that doing nothing is also a choice. And in this case, it means accepting that the most successful theory in physics cannot explain why it works at all. Attempts to resolve the imbalance have produced proposed fixes, but none settle cleanly into place. Each solution that restores matter comes with consequences that destabilize something else. The problem does not close, it shifts. Introducing new particles often requires energy scales far beyond current experiments. These particles explain the past but become unreachable in the present. Their absence today is not evidence against them, but it is not evidence for them either. Allowing symmetry violations at extreme conditions raises deeper concerns. If foundational symmetries can fail selectively, then the reliability of extrapolating laws across scales becomes uncertain. Physics gains flexibility but loses rigidity. Cosmological explanations avoid modifying particle laws, but at a cost. If our universe is only one outcome among many, then explanation turns statistical. Existence becomes typical, not necessary. That reframing weakens the idea of a single, complete description. What remains unresolved is not a lack of imagination, but a lack of convergence. Theories multiply, but none collapse the uncertainty. Instead of approaching a solution, physics circles a stable contradiction. The imbalance that allowed everything to exist still resists containment. It fits nowhere comfortably. And every attempt to force it into place reveals another stress point in the structure, meant to support it. What makes this problem endure is not its mystery, but its precision. The universe did not violate the rules loudly. It followed them closely, faithfully, and still produced an outcome they cannot fully justify. That quiet compliance is what keeps the pressure alive. Science is accustomed to anomalies that break models and demand correction. This is different. Here, the models perform exactly as designed, and that performance leads directly to an incomplete explanation of existence itself. Success and failure are intertwined. The resurfacing theories are not revivals of discarded ideas, but responses to a narrowing landscape. As experimental margins tighten, uncertainty does not shrink. It becomes more defined. What remains unexplained becomes harder to dismiss as temporary ignorance. This has shifted the emotional center of the field. Confidence has not collapsed, but it has become conditional. The question is no longer whether the laws work, but whether they are sufficient to describe why anything works at all. There is no final contradiction announced, no declaration that physics is broken, only a recognition that the foundations are under sustained load. And that load has not been relieved by time, data, or refinement. The pressure remains because the universe exists in a way it should not, according to its own most trusted rules. And until that tension resolves, uncertainty is not a failure of knowledge. It is the most accurate description science can offer.